I don't know how many videos I've mentioned bond polarity in, but it feels like all of them. It is important for us, again, to run through that hierarchy of vocabulary terms. We had the idea of what it means to be polar, right, in any context, which would be some version of uneven, right? And if we have a polar bond, we have a bond where electrons are shared unevenly, right? Right? And so another way you could say that is uneven charge distribution, which is terminology that we want to utilize more. And then we can have a nonpolar bond, which is a situation where you have evenly shared electrons, right? That is a uniform charge distribution. Which brings us to one last vocabulary term in this set, which is a dipole. Right? When you have something that is polar or uneven, if you have two opposite poles, two opposite ends, like magnetic north and magnetic south on the Earth, you end up with a dipole. This is when you have two opposite ends. And we are rapidly approaching the point where we're going to tie together our three-dimensional structures and our intermolecular forces. And in order for us to do that efficiently, we're going to need some shorthand notations for dipoles. There are two of them, the first of which is delta notation. In delta notation, we use, unsurprisingly, the Greek letter delta, which looks kind of like a music note. That's okay. And we put a plus sign on it, or we put a delta with a minus sign on it. Those are theoretically the same thing, one with the plus and one with the minus. So what do these things mean? Well, what we have here with a delta plus is that we have a slight positive charge, right? We could say it's partial. And with a delta negative, that's a slight negative charge. And so what is the importance of that? Why not just put like a plus or a minus on them? And there's a very good answer, and that good answer is these aren't ions, all right? An ion gets a plus or a minus charge. These dipoles get slight positives or slight minuses. They're partial charges. So that's something worth noting, is that these are not charges, right? They're not ions. That's what I really mean there. They are partial charges. Maybe I should put this full charges, if that is indeed a vocabulary term. All right, so delta is one way that we show this. The other common way to show it is using arrow notation. And I do want to leave a little room right here, so arrow notation uses vectors. And if you've taken physics, a first-year physics class or whatever, vectors are things that have magnitude and direction, like 33 miles an hour eastbound would be a vector versus 33 miles an hour would be a scalar quantity. Well, a good way to show both magnitude and direction is to use arrows of different sizes. And that's what we're going to be doing here. These point from the slightly positive end to the slightly negative end. And the way that looks is we draw our arrow pointing at it, and then we put this extra line on this side, which I'm more than happy to declare that side is slightly positive, so it gets a plus sign, right? It's like a little plus sign over there. One thing that I do want to distinguish here is the idea that delta notation is usually for individual dipoles, Well, arrow notation is usually for net dipoles. All right, and you'll see what I mean by that as we tie this together with our three-dimensional structures. A commonly asked question is, how do you know which atom gets the slight positive or slight negative? And there's a surprisingly simple answer. The atom with the higher electronegativity is better at attracting electrons, and it will get the slight positive, all right? So, sorry, the slight negative. So, slight negative atom with the slight negative is the higher electronegativity, whereas the atom with the slightly positive charge is the one with the lower electronegativity. All right, so in this case, it points at the higher and it starts at the lower. And we'll get more into how those vector arrows work, not in too much detail, but before we do that, I want to take a look at how these electron densities move around. Electronegativity is one of those words that I hope you're tired of hearing because I say it so often. That means there's some level of importance to it, right? Electronegativity. Which I abbreviate E-neg, and that's not a super legit abbreviation, but it does save me a fair bit of writing. This is a measure of an atom's ability to attract electrons. For our purposes, we've just been grabbing the electronegativity values off of the periodic table, and in this particular periodic table they're on the bottom right. You can remember the trend is that it increases as you go up and right and decreases as you go down and left, so just keep those in mind. But I want to see how this works in terms of the pictures. I've described in a previous video that a bond, at least a covalent bond, but bonding in general, are approximately a tug of war between atoms, and what they are fighting over are the electrons. In any real-world tug of war, theoretically you have a winner, so theoretically one side is stronger, and in this case we're going to say that that side has the higher electronegativity. So we can stronger, right, for our purposes is going to be higher electronegativity. So the stronger side in a tug of war would pull the rope closer to them. The stronger side in our tug of war here is going to pull the electrons closer to them. And then our weaker side is our lower electronegativity. And then this starts to make sense in a real-world context if we look at an example maybe. So we'll pick something simple, maybe HCl. Hydrogen, and we've drawn this all out before, but 2.1 for hydrogen, 3.0 for chlorine. If we draw it out, we're expecting a covalent bond, and we see something like that. Now, in reality, the chlorine has the higher electronegativity. It is better at attracting electrons. So the electrons involved in this bond are going to be pulled closer to that chlorine. And there is a consequence, all right? Electrons are negative. If chlorine is pulling the electrons closer, it's pulling the negative charge closer, and it's starting to become a little bit negative, just like we saw right here. The higher electronegativity goes with the slight negative charge. It is stronger, it is pulling electrons closer, those electrons are negative, so it starts to get a little bit negative, a partial negative charge. And on the opposite side of that, hydrogen is now farther from those electrons. They've been pulled to chlorine, and so it starts to get a little bit positive. It is distanced from that negativity. The analogy I always give in class is like Your parents have probably said to you, oh, I don't want you hanging around with those kids because those kids do bad things. And I am worried that if you surround yourself with those kids who are doing bad things, you're going to start to do bad things too, right? Well, it's happening right here, which is when this chlorine surrounds itself with electrons with negativity, it starts to get a little bit negative. And when that atom has distanced itself from that negativity, it starts to get a little bit positive. That's what your parents are hoping for you. That's what your parents are hoping to avoid for you. Let's look at this maybe a little messier on another piece of paper in terms of electron distribution. I've never done it before. We'll give it a try. As a quick note, we should probably draw in our individual dipole, but with an arrow notation, it points from the slightly positive to the slightly negative. Okay, so we don't want to forget that. This is the net dipole for this molecule. It's polar, but we generally wouldn't want to use this for just individual dipoles. Not an issue here. I'm just going to draw out two generic atoms. In fact, I'll pick some atoms and we'll look at H2 versus maybe like HCl, maybe even something like NaCl. And we'll talk about our electronegativities and how that affects the electron distribution. So hydrogen has an electronegativity of 2.1, 2.1, 30.0. Again, I'm pulling those from a periodic table, 0.9 and 3.0. When we draw these, I'll draw this hydrogen first, and size is not going to be to scale, so don't get yourselves all excited. But I'm just going to draw one of my atoms there, and one of my atoms there, and I'll do the same thing here and here. And what I want us to look at are the electrons in between them, right? So this has equal electronegativities. In fact, we're going to say that this is non-polar, right? Because the electronegativities are the same for both. So our electrons involved in that bond are going to be equally distant from each of those hydrogens. As we look at the next one, where we have hydrogen as a 2.1 and chlorine as a 3.0, I know, should have done it in green. Chlorine is stronger, those electrons are going to be closer to it. So when I draw them in, I'm going to draw those electrons there. And then if we have something like NaCl, we don't even have shearing. With a difference of 0.9 and 3.0, we end up with a situation where there is a give and take, where sodium ends up a plus, and then chlorine ends up a minus because it got both of those electrons, and that sodium lost one. So equal shearing, nonpolar, unequal shearing, polar covalent, and then no shearing at all, give and take, that is ionic. Might be useful to write that down. So this is nonpolar, covalent, shared equally, polar covalent, and then ionic. And all that's changing is your electron distribution, your charge distribution. And I'll try and draw that in. But in this case, we're looking at the electrons are not locked in place right there, right? Those electrons are moving, but in the big picture, they're moving uniformly within that area. In this particular case, the electrons are moving, but they're spending more time by the chlorine, so the charge density is going to be higher on that chlorine. We're going to have more of the electrons spending more of their time over there. And then over here we have this situation where the electrons are just plain over there, making it negative. And we can draw in, before I forget, our arrow notation on these. So we wouldn't expect deltas here. We would expect the electron to point in that direction. And I'm not going to put in an arrow or a delta on an ionic compound, but quite assuredly it would point that way. We actually have charges here, right? So this would be our slight negative and our slight positive. And we'll go into a lot more labeling of dipoles once we finish our discussion of three-dimensional structures.